Well, hello. Today we'll start a new chapter. We'll be on transformations. This section, we're going to go over translations again. We've already looked at some translations. And I think we already know a lot of the things that we need to know about translations. I think you already know that the result of a transformation is called the image. If all I drew was these two, there'd really be no way for you to know which was the image and which was the pre-image. So I'm telling you, this is the pre-image and this is the image. How did we get from one to the other? Well, we shifted 3 units to the right and 1 unit up. We used to write something like xy goes to, in this case, maybe x plus 3 and y plus 1. There's another way to write that now. We can just write, suppose we just wrote the vector 3, 1 and called that our translation. That would pretty much tell us the same thing, wouldn't it? 3 units over and 1 up. We could say that xy goes to x plus 3 and y plus 1. That's kind of the long way of saying it. This is like shorthand. This says, look, the x's and y's are implied. All that really matters is how much we shifted, and the shift is represented right here. What's the difference between a point and a vector? Well, if the tail of the vector starts at the origin, 0, 0, the representation is identical. For instance, the point 3 minus 3 here. Well, if we connect it, that's also the vector, except it's supposed to be a straight line. The vector 3 minus 3. But that's because we started at the origin. In more advanced math classes, you will frequently refer all vectors back to the origin. It makes them easier to add and to work with, basically. But it doesn't have to. For instance, I can start a vector here and say that's the tail. And that's the end. And then when I connect them, I will still use the components to define the vector. In other words, this vector represents, in a sense, a displacement of 1, 2, 3 horizontal units and 1 vertical unit, or 3 x units and 1 y. And something like this, you can see that, suppose I wrote this. Well, if I put the head here, the tail back here, I want 3 units along x and 1 on y. But vectors are directional. So this is actually the vector minus 3, 1. Because we went backwards 3 units and then up 1. And of course, if I'd gone here and wrote a vector that came to here, like that, well, that would be minus 3, minus 1. So vectors are directional. If we need to, I don't remember if this is in this section or not, but as long as we're talking about vectors and it's so simple, might as well go ahead and show it to you. Suppose I had the vector 3, 1, and then I've got the vector from here to here. So it's 2 units this way and 2 units this way. So we'll call this the vector 2, 2. Suppose I want to add this vector to this vector. Well, that's where referring them back to the origin intuitively makes a bit more sense. We can certainly add these 2 vectors, no problem, even the way I drew them. But when we end up with a result, what does it mean? First, what does it mean when we add these two vectors? Just add them up component-wise. You can almost write one under the other, like this. Pardon me, that's supposed to be a 2. And then just add them up. 3 and 2 is 5. Just don't ever carry a thing from one comma to another. For instance, if this were 8 and a 3, that would be 11. You don't put a 1 here, then carry it over here. You just put an 11 here. And this is 3. So the resultant vector, if we add these, is 5, 3. But where do I put it in order to get a more graphic representation of what we just did? Well, that's where it comes in handy to refer things back to the origin. Because now, suppose I had a 2, 2 vector. Boy, it's getting way too crowded, isn't it? Let's just draw the 5, 3. Here's 5, 3 right here. Well, if we had a 2, 2 vector here, and a 3, 1 vector here, and added them up, we'd get 5, 3. All we do is add up the x-coordinates and add up the y-coordinates. So if we go 3 units over and 1 unit up, and then 2 units over and 1 unit up, that puts us right here. I redrew these so they don't look quite so messy. Now if we have 3, 1 down here, and 2, 2 here, and remember, this is the point 2, 2, so the line going from these arrows, it's normal to put an arrow on a vector, even though this doesn't mean that it's a ray that takes off to infinity. This is in fact the vector. But normally you do put an arrow on a vector. That's not to indicate that it's a ray. It just tells you which direction it goes. Because, see, this is the vector 2, 2, because it goes from here to here. Suppose I put minus 2, 2. Pardon me, minus 2, minus 2. Well, this would be the same, all the same line. It has the same slope. It would be a continuation of the same line. But they're two different vectors. I know that's a little bit confusing, but you just gonna have to bounce your brain back and forth between rays and vectors and understand from the context what it is we're talking about here. So this segment with an arrow on the end of it, that doesn't mean it's a ray that goes off to infinity. It is definitely a finite vector. But we don't really call them segments anymore. For one thing, segments don't have direction. And all the time we talked about line segments, we never really talked about a direction. We talked about the length. Well, vectors have length and direction. The ordinary numbers, that's like this is our number line right here, the x-axis. You can always just think of that as the real number line. These have nothing but lengths. That's all you can say. But when you start talking about vectors, we've got a length here. We don't know what it is yet. We can figure it out from the distance formula, the distance from here to here. But it also has a direction. That's what makes vectors so special. They're not just numbers. They're numbers with directions attached to them. And that makes them extremely useful and, of course, more complicated. For instance, this resultant vector here, this is the vector 5, 3. We just algebraically added up these two vectors and got 5, 3. And that is the correct sum of these two vectors. But there's another way to look at this. Suppose we're going to add the vector 3, 1 and the vector 2, 2. There's another way to look at the addition of vectors. Suppose I take this vector here, which I'm going to add to 3, 1, and just pick it up. Okay. Pick it up and move it. And attach it to the end of the vector 3, 1. In other words, I follow along 3, 1 here, and then I walk along another vector, the 2, 2 vector. And where do I end up? Of course I end up at 5, 3, which is the sum of 3, 1 and 2, 2. So this is another way you can look at vector addition. You're just putting them together, tail to tail. Tail of this on the head of this, and you end up here. If I added up another vector, I could stick it on the tail of this one, or pardon me, the head, and continue like that. We can add as many vectors as we want. This is a graphical interpretation of what it means to add vectors. Just as when we add numbers on the number line, we're really adding distances, aren't we? If I say, what's 3 plus 2, I can go to 3 here on the number line, and then 2 more steps, and I'm at 5. And that tells me that 3 and 2 is 5. Exactly the same thing here. I add up the vectors by just putting them together. The only difference is they aren't always horizontal now. I have to maintain the same direction. Notice that this is a reproduction of this vector. It has the same direction and the same length. That's, of course, is what a vector is. It's important to get both of them the same length and the same direction. When you put them, string them together like this, you end up at the same point. And that is, in a sense, why this vector is the sum of these two. So all those triangles we had, if you think of them as vectors, then you can always think of one side as the sum of the other two, or perhaps the difference. For instance, this one here you can think of as going out along 5, 3 and then back along 2, 2, and that would leave you at 3, 1. And of course, if you went out along 5, 3 and subtracted 3, 1, you'd be moving along this vector and end up right back here at 2, 2. So when you add and subtract vectors, you're in a sense adding and subtracting displacements also. Think of it that way if you like. You've displaced this point from here to here, and then displaced it again from here to here. Yeah, I didn't mention it, but when we write these as ordered pairs, that's called the component form of a vector. And it's really the most useful way to write a vector. There's sometimes in other math classes, you'll see something like V for velocity, but you'll see that over it, that little half arrow and thing. That means this is the vector V. That's not a component representation and doesn't tell you anything about the size or direction of the vector. But that's okay, because this is more of a variable form of a vector. In other words, when we write x, that just takes the place of some real number. 3, that's a real number. X, that's just a variable that stands for some number. Maybe 3, maybe some other real number. It could be any. Same thing with this. This is usually the variable representation for a vector. There are other ways to do it, of course. If you see the expression x comma y, well, that's a variable expression for a two-dimensional vector also. And I think we're only going to look at two-dimensional vectors, but you might keep in mind for other math classes that there are certainly more than 2 dimensions. So there are, of course, higher dimensional vectors also. For instance, in the real world, if you wanted to use a vector to show the trajectory of, say, a ball, or say a cannonball that got shot out of a cannon, your vector would be 3-dimensional. You have your xy coordinates, say, on the ground, but then there's the height also. We're mostly just going to look at vectors in a plane, as if they were just on a flat surface. So here we are back at our original triangles, which have been translated. Pre-image and image. Translation, as we remember from previous chapter, simply moves the object, in this case a triangle, a set number of units in the x direction and in the y direction. And every point is moved the same. For instance, this moves 3 over and 1 up. So I could simply write this as the translation 3, 1. That pretty much tells us everything we need to know. This point moves over 3 and up 1. This point over 3 and up 1. Every single point over 3, up 1. Every single point in the pre-image moves 3 units in the x direction and 1 unit in the y direction. When you do that, you don't change the object. This is what we used to call a congruence transformation. Now, for no good reason, we're going to start calling it an isometry. I think that's the right way to pronounce it. I looked it up, the accent is on the som, so it's definitely isometry. I just don't know if it's isometry or isometry. My English dictionary is pretty cheap. It doesn't list pronunciations. I had to check my math dictionary. I know, that's weird. The English dictionary doesn't have a pronunciation in it. The math dictionary, which is more about concepts and abstract ideas, actually has the pronunciation in it. Except that it only gave me the accent and didn't really say whether there was a straight line or a curved line over the O, so I don't know if it's soft or hard. It's not a word I use very much, to tell you the truth, obviously. But we need to know what it means. It'll be on the standardized test. If you haven't seen it, it looks like this. ISO, remember, equal. Isometry. Kind of like isometric, I guess. Probably pronounced along about the same way. That just means that the transformation, in this case a translation, does not affect the size or shape of the original figure, or a more mathematical way to put it would be that all the angles and sides are maintained. Sides don't change length, and the angles don't change either. Well, oops. Here we have an error. What's the mistake? We're supposed to be translating the quadrilateral EFGH. Here we go, EFGH. And that goes to x minus 1 and x minus 2. In vector form, we could just write minus 1, minus 2. That's our translation. Well, let's see here. Minus 1, minus 2 would be that way. What did he do? He went, oh, I see. He was making a common mistake. You shouldn't do geometry standing on your head. It's good for the circulation, but it causes confusion. He was supposed to go back 1 and down 2. Instead he went forward 1 and up 2. So if he just turned around and sit properly instead of standing on his head, I think he'd have gotten this problem right. That's the only thing wrong. He just went the wrong direction both times. It should have been to the right one, it should have been to the left one and down 2. Instead he went to the right one and up 2. And here's one where we're just going to translate a point. And it's really no difference between translating a point and translating an object. An object is just a collection of points, and every single point is translated exactly the same way. So translating a single point is equally instructive. What is this? It goes from xy to x minus 3 to x plus 2. So if we wanted to, we could rewrite this translation as the vector minus 3 plus 2. I just like to think of it that way because now we could do it graphically. We can go minus 3, which is going to be tough, and over to jeepers. I had to change grids so that we had a little room. Everything's taking place way down on the bottom here. As I was starting to say, there's a couple ways to do this. Number one is the nice simple way, where we start where we are and apply this vector using our tail-to-tail method. So where's the vector? Here we are at a point 0, 8, which, by the way, we could also think of as, pardon me, that's 0, minus 8. If you think of the origin as the origin of your vector, as I mentioned before, you can also think of this as the vector 0, minus 8. And if we were to add 0, minus 8 to minus 3, 2, well, there's the graphical way of doing it, which is we take the vector minus 3, 2, which is minus 3, and then up 2. And we end up at the point minus 3, 6. Pardon me, minus 3, minus 6. Right here. Well, we could have also just written minus 3, 2, and we add that to 0, 8. Doggone it. I mean, 0 minus 8. Something wrong with my mouth today. It just doesn't want to say minus. Now, where we go, it's 10 on this side of the our y component. Wow. This is 2 minus 8, which of course is minus 6. And this is, it's 2 plus a minus 8. That's what I mean to say. Which of course is minus 6. And we have minus 3 plus 0, which is minus 3. So the point is, if you know the coordinates of the points that you're transforming, or in this case translating, and you know your translation vector, you can just take the point you're translating, add your translation vector to it, and you've got your new image point. This is the pre-image point. This is the image point. So you can do it graphically by doing exactly what they say here. Go backwards 3 and up 2. No, pardon me. Or you can just add the two vectors together. Sorry about that loud sound. Without thinking about it, a fly flew in front of me. Don't know how he got in, but I smacked it without thinking about it. Sorry. Now we have a rectangle. We're going to translate it, and then we're going to find the area. So here's the pre-image. This is the image. Notice that it's 3 units wide, but we moved it 3 units, so they're kind of right next to each other. We also went 2 units down, so minus 3, minus 2. What's the area of this one? Well, 3 units wide, and what do we got here? 4 and 3, 7 units long. So that's 21. And over here, it's 3 units. I don't know why we even have to do the multiplication. This is 3 by 2 and 5 is 7. This is 3 by 7. We haven't changed the dimensions, so how in the world could we change the area? With this QRST as the pre-image, all we've done is taken this and shifted it. Notice when I move this thing around, I'm not changing the shape. There's another way you could look at it that would be kind of advanced, I guess. Anyway, you can see that, suppose I just had to move this like 5 units to the left. Well, let's see here. Here's 2. Had to put us over here. If it was 10 units to the left, well, I'd go from 2 to -8. And it'd be like that. It's no big deal. Why doesn't the area change? Well, let's put this off to the side and forget about it for a minute. We have formulas for area. For instance, length times width. Well, where does the position come into that formula? In other words, I've got this, say, rectangle. It's right here, and I compute the area. Now, when I move it over here, where in my formula for area do I take into account the position of the object? The answer, of course, is nowhere. The position of the object, whether it's here, 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 could be off the page. Nowhere does the position enter into the equation for the area. And if it's not explicitly part of the equation, then it doesn't count. That's one way to look at it. But there are no area formulas which depend on the position of the object. Therefore, how could a translation possibly make any difference in the area? Same thing's true for perimeter. Where in your formula for perimeter do you take into account the position of the object? Nowhere, because it's completely irrelevant. The area, the perimeter, these things are all independent of position. So moving the object around like this, gee whiz, what's wrong here? There we go. Move it around all you want. It's, as far as perimeter and area are concerned, it's irrelevant, because those measurements are the same no matter where you put the object. Now, this one's a little bit different because we have a variable in here. It's not just a set number that's being shifted. How much it gets shifted depends on where we are. The higher it is, the more it's going to get shifted, because the larger the y component will be. Now, if we want to put this transformation, into vector form, well, x goes to x plus y, so that's y, and then y doesn't change. So if we want to write this transformation as a vector, it's y0. That's all we have to do to find our new points, for instance, a prime. We add the y component to the x component to get the new x component, and the old y component is left alone. B prime, same thing. We get 6. There's supposed to be a comma there, and then 2. And C prime, well, that's 4 and 3. It is 7 and 4. So, what's our new triangle? A prime is 4, 2. That's this one right here. B prime, 6, 2. Okay, that's right there. C prime, 7, 4. Well, that triangle sure doesn't look like an isometry. This transformation doesn't look like an isometry to me. But let's look at this from a translation point of view. What translation did we apply to this point? I guess I'll just write it over here. Put a little colon here. The translation we applied was 2, 0. The translation we applied here was 2, 0. but the translation we applied here was 4, 0. Which means this transformation is not a translation. Well, it's certainly not a isometry anyway, because in a congruence translation, also called an isometry translation, every point is translated along exactly the same vector. Here we got the vector 2, 0, 2, 0, but this messes us up. If this was 2, 0, we would have an isometry, and our image would be congruent to the pre-image. The areas, well, I'd be amazed if they were the same. And for one thing, it's pretty obvious this is an isosceles triangle. These sides go from x equal to 3 to x equal to 4 and x equal to 2. That's 1 unit to the right or 1 unit to the left, and down 2 units. So in a sense, these are almost the same vector. This is 1 unit to the right and down 2, 1 unit to the left and down 2. Pythagoras would say that the length of those was 1 squared plus 2 squared, or 1 squared plus 2 squared. Same. So this is an isosceles triangle. However, this doesn't look much of anything like an isosceles triangle. We have 2 units here. Well, the change in x is 1 unit, and this is 2 units. So 1 squared plus 2 squared. Take the square root of that, you're definitely not going to get 2. And this here, well, that's just right out of the park. That's not going to be anywhere near 2. Or this here, either. This is an isosceles triangle. You can probably tell just from, as they say sometimes, you can tell from inspection. This is not an isosceles triangle. We have definitely changed the triangle. It's not a congruence transformation. It's not an isometry. And the reason is really apparent if you just do it this way. These vectors here all have to be the same. If we don't move each point according to exactly the same vector, then we don't have isometry. Now in this one, we're going to take a look at what happens when we translate a line for which we have an equation. So what happens to the line, and what would the new equation be? Well, I went ahead and rewrote this so that we have the kind of function you're used to seeing. It's also much easier to graph. We can rewrite this as y equals 4 minus 2x. That's this line right here. Maybe I should just write it in. Naturally, b here is 4. So this is our standard equation for a line. Y-intercept is 4. X-intercept is 2. Makes sense? So, the point 2, 0 is on this line. What happens when we translate the point 2, 0 under the vector, or translation if you prefer, minus 5, 4? Well, what we're going to do is go 5 units this way, 2 minus 3, and then up 4 units. In other words, the point 2, 0 becomes the point minus 3, 4. It didn't just slide over like that. It looks like we just took this line and shifted it over. Well, that's because lines are, if I put little arrows on them there to show that in reality these lines go off to infinity in both directions. Any increase along the line here is kind of unnoticeable, isn't it? This point right here didn't come from here. It came from a point 5 units over and 4 units down, which would be right here. In other words, this point came from here. We went over 5 and up 4. Well, this is our new line here, and I just drew this line simply by doing what I just described to you verbally. I took this point, figured out what the new point would be, and then just grabbed some other arbitrary point, it doesn't matter, say this one, and over, plotted the 2 points, and then drew a line that went through them. After all, you only need 2 points to plot a line. We also only need 2 points to figure out the equation of a line. Or 1 point if we know the slope. The slope of this line is 2. Pardon me, minus 2. We don't even need to check it because it says so right here. Remember, the part in front of the x is going to be the slope. If you rewrite it in this notation where y is on one side and all the stuff that's equal to y is on the other. This is more like your functional notation. In other words, you might remember this is f at x equals 4 minus 2x. Same thing. This does not mean that the slope is 2 because the coefficient of x is 2. This isn't written in the standard form for a line. This is the standard functional form. So the coefficient for x gives you the slope. What about this line? Well, here's 2 points on the line. 1, 0. And here's another point. 0 minus 2. So what's the slope of this new line? Well, we call this P1. We've got the change in y. That's 0 minus a minus 2. How about we just call that 2? I'm not sure if I said minus 1, 0, but I wrote 1, 0, which of course is wrong. So we've got our numerator, 0 minus a minus 2. Minus 1 minus 0. That equals minus 2. So the slope over here is also minus 2. What's the equation for this line? Well, that's pretty easy to figure out. All we have to do is pick one of these. How about this one? Looks pretty easy. And start with, I guess I can go ahead and write over here on the graph. Y equals minus 2x. We already know that has to be in there because we have a slope of minus 2. But we don't know is b. Now let's try the point minus 1, 0. We can write that 0, that's the y, equals minus 2 times minus 1 plus b. Well, this is just going to be 2. Plus b, or b equals minus 2. So the equation for this line over here would be y equals minus 2x minus 2. Now, you notice anything about these two equations? Maybe if I wrote them differently, it would, if we rearrange this, this is 2x minus 2 over here. Suppose minus 2x minus 2. And this is minus 2x plus 4. Notice the only difference here is the y-intercept. Our b here is minus 2, and over here it's 4. Which means, in a sense, we just shifted our line down 6 units. Well, that's kind of weird, isn't it? How would a line which is translated according to the vector minus 5, 4, meaning it went to the left 5 and up 4, the equation of that line, it's just the same line dropped down 6 units. It's kind of weird, isn't it? And they also ask you to compare the slopes. Pardon me, we already did that. I meant to say the y and x intercepts. Here it's 4, here it's 2, which means we dropped down 6. This is 2, where the line intersects the x-axis, the x-intercept. Here it's -1. So we have a vector, -5, 4, and yet the y-intercept changed by 6. It went down 6, and the x-intercept went to the left 3. What in the world does that have to do with -5, 4? Kind of weird, isn't it? In this part, they want us to write an equation without taking a look at the graph. Just algebraically figure out what the equation for the new line would be after the translation 2 minus 6. Now we just did it for one particular line and showed that the slope for the translation, the slope of the image, is exactly the same as the slope of the pre-image. Well, that's always going to be true, and we might as well just show that it's always true right now. What we're going to do is take 2 points. We'll say x1, y1, and then x2, y2. Now, if these are 2 points on a line, you want to know the slope. We already know that's y2 minus y1 over x2 minus x1. Suppose we translated both of these points under the vector AB. Suppose we apply this transformation to both of these points. In other words, 2 points on a line are going to be shifted according to the translation AB. What will the slope of that new line be? Well, x1 becomes x1. Let's start with the y's, I guess. It would make more sense, wouldn't it? y2 becomes y2 plus b. And y1 is y1 plus b. And down here at the bottom we have x2 plus a, that's our new translated point, minus x1 plus a. That's our other new point. What happens when I drop the parentheses and expand this out? Well, I get a b over here minus y1 minus b, so the b's cancel, and I get y2 minus y1. Over here, same thing, minus x1 minus a, the a's cancel, x2 minus x1, but that's just what I had over here, isn't it? So when we translate a line, the slope won't change. Now that we know that, we can come up with an equation for the image of a line under a translation without actually graphing it, because we automatically know what the slope is. So for part C, we really only need 1 point, because we already know the slope. So what would 1 point on our new line be? Well, that's easy. Let's just pick, say, the y-intercept. That's always an easy one, where x equals 0, then y equals 4. So where would the point 0, 4 go? Yeah, I can just draw it right here, I guess. We've got a point 0, 4. It's on the original line, the pre-image, and it goes to under the vector 2 minus 6, it goes into 2 minus 2. This is a point on our new line. And we already know the slope is minus 2, because if we write our, well, it's written right here, isn't it? Y equals minus 2x plus 4. In this case, we have the y, which is minus 2, equals minus 2 times x, which is in this case just positive 2, plus b. We don't know what b is yet. That's what we're looking for here. Well, we got minus 2 here, minus 4 here, plus b. We add 4 to each side. I think we get that b equals 2. And our new equation will be y equals minus 2x plus 2. Notice that the relationship between our shift, our translation, and our new equation is not immediately obvious. Later on, probably in an next algebra class, you'll learn a lot more about shifting functions. And after all, this line is just a function. It's an extremely simple function, but it's a function. It's a linear function, in fact. There is a definite relationship between the vector you're using, or you could say the numbers, the x number and the y number you're using for the translation, and the equation for the image of the line. But it's not immediately obvious. You can fool around, see if you can figure out what it is. Well, that's about it.